We're going to do two things today. We're going to do latent growth curve modeling with covariates using Mplus. We're going to do a multiple group version of that model, and we're going to do a covariate. So let's get started. The input file I want to use is called LGM with X. So start up your Mplus. And Mplus starts you off with this blank input file. I'll close that, and I'm going to open up the folder where I've got these things stored. And here's my input file here. I'll open that up. And let's put that on the screen with something I can blow up the text size. Okay, does everybody have it? So Mplus input statements run one analysis at a time. Mplus input statements run one analysis. The syntax file is broken up into different command statements. Here we have an Mplus input file with 4 commands: title, data, variable, and model. This is an input file that's mostly copied out of the Mplus user's guide. This input file and data we're going to use come from example 8.8. And just a reminder, you get all these input files and data files with your Mplus installation. The title block, you can put any text in here. You don't need to terminate it. It can be as long as you'd like, and you can keep track of what you're doing. We're going to do latent growth curve modeling with covariates using Mplus User's Guide example 8.8 data, but we're not actually doing example 8.8 today. The next command is the data command. In the data command, we identify the file that contains the data we're going to use. And here's the file that I've processed a little bit from the Mplus User's Guide, and it's called ex0808.csv. And then the next command is a variable command where we tell Mplus information about variables in the data file. This first subcommand is called names, and this is where we identify the variable names of the data in the file. And it's important that we get this string correct, because this is the only place Mplus knows what the right variables are. So in the data file, there's no variable name in the first row. The first row of the data file is data. So when you prepare your data for Mplus, you need to keep track of the order of the variables and what column corresponds to what variable. The data file actually has 8 columns of data, including G, 4 Ys, X, and it also has CG and C. We're not actually going to use variables CG and C, so I left them out of the name statement. You know I've left them out of the name statement because there's an exclamation point on the line here, and everything that falls to the right of a exclamation point Mplus will ignore. That's the common character in Mplus syntax. And then I put some notes in the syntax file here just so you can help keep track of what we're doing. And you can put these notes here, the comment character on the front. So here, this is an exclamation point, so Mplus will ignore this, and I'm just reminding myself that G is binary, Y1 through Y4 are continuous, X is continuous, and CG is the same as G. but instead of going 0, 1, it's 1 and 2, and C is predicted G, and we'll talk later about where those variables came from and what they mean in a later session. So this, for example, could reflect data from a study where we have 4 repeated observations on our research participants, and they're Y1, Y2, Y3, and Y4. We have a grouping variable, G, and we have a continuous predictor variable, X. So these might be repeated measures of depression, male-female indicator for G, and an age variable in X, for example. The real exciting stuff happens in the model statement. In the model command, we have a first aspect of our model is this so-called shorthand notation for a latent growth curve model. This is asking Mplus to give us a linear growth curve model with an intercept and a slope, and by default Mplus will freely estimate variances on the intercept and the slope, and it will estimate by default residual variances for each of the y's, and it will allow those residual variances to be different from one another. We know it's linear because the time steps here are going up in equal intervals at 0, at 1, at 2, at 3. That means that we're assuming those intervals are the same for every person, and they're equally spaced across the repeated observations. And the decisions about what those time steps get fixed to is driven by the design. And I say fixed to because this is the Mplus notation for a fixed parameter, the @ sign, followed by a number. And then finally, the next command here is a regression of the intercept and slope factors, or random effects, on G and X. So it's just regression. And what this will do is tell us how the starting level and the slope differs by G and differs by X. Also notice that even though G is binary, we don't need to declare it as categorical. Mplus has special routines for categorical dependent variables, but it does not care binary or continuous independent variables, predictor variables. If you have a categorical variable like race, black, white, Hispanic, to use that variable in Mplus, you're either going to need to break that into a pair of binary dummy variables or do multiple group modeling, which we'll work through later today. So Mplus does regression with predictor variables, and always what you get are the increase in the dependent variable per unit increase in the predictor variable. It doesn't set up any special contrasts for you automatically like you might with Mplus. So you need to dummy them out. Okay, so that's our input. Let's go to our Mplus program and see if it will blend. So the first thing we get in our Mplus output is a little note that the Mplus reading terminated normally. That means we didn't have any errors in our input statement. Next, we're going to get information about the particular analysis we run, including the number of groups, which is 1. You'll know what that means by the end of the session today. Number of observations is 1,000. So there's 1,000 pieces of data in this data set. We have 4 dependent variables, 2 independent variables, 2 continuous latent variables. That sounds right because that matches what I wanted to get Mplus to do for me. Here's our continuous dependent variables, our observed independent variables, and continuous latent variables. Some technical information about the estimation. We're doing maximum likelihood estimation. Then we get just a little repeat about what the input data file was. Then we get this wonderful little comment that the model estimation terminated normally. You always want to see this. You won't always see it. And when you don't see it, you need to figure out why and get it to go away. In the model fit information, we have things like information criteria, which can be used to test or compare non-nested models, log likelihood values, which can be used to get p-values for model comparisons that are nested. Also, the chi-square test can be used to evaluate overall model fit and used for chi-square difference testing to test nested models. And the root mean squared error of information and the CFI and TLI are good indicators of model fit. And we'll cover how to interpret those aspects of model fit in a later session, but these are all indications of a good fitting model. So now we have our model results. The first part is we have our what I call the measurement model of the latent growth curve parameters. That's because these are factor loadings, but they're fixed and they're not estimated like factor loadings usually are. We know they're fixed because they have standard errors of 0 and the estimate over the standard error on these 999s. That's our clue that these are fixed parameters. The reason why you want to just judge by SEs of 0 is because Mplus only gives you out to 3 decimal places of precision. So sometimes you may have a really low standard error. It looks like 0, but it may not be fixed, and you can tell if the estimate over the standard error is some non-999 value. Here we have our regressions of intercept and slope on our grouping variable and our continuous predictor variable. Here we have the regressions of our slope on our grouping variable and our continuous predictor variable. Now the regression of the intercept on the 2 covariates tells us how much the outcome variable differs at baseline. The effect of G here, this is an ANCOVA type regression coefficient. This tells us the mean difference in Y at baseline, estimated given this linear model. So when G is 1 versus when G is 0, the mean is 0.512 units higher. Here's our standard error. Here's our z-test for that difference and a p-value for that difference. So there's a big difference in the baseline value of Y according to G. Another way of saying that is per unit increase in G, there's a 0.5 difference in Y at baseline. And that's because G is scored 0, 1. So a unit increase means from going to 0 to 1. Similarly, when we interpret the value of X, we say that for every unit increase in X, which could be going from 0 to 1 or -1 to 0, there's a 0.885 difference in the baseline value of Y, and that's also statistically. So the slope parameters are analogous to interactions between a time factor and a baseline variable. So if you were doing something like proc mixed, you would be fitting a model that was a intercept, the main effect of the predictor variables, and then the interaction of the predictor variables and the time variable. That's the same quantity you're getting here with these regressions of the slope on the predictor variables. And here we have the regression of slope on our binary predictor variable. And this is saying that the pace of change is 0.279 units higher for every unit increase in X. Or when X is 1 versus when X is 0, the slope is 0.28 units higher. And similarly with the X, we have for every unit increase in X a 0.425 higher level of the slope variable. And both of these are significant. Beyond that, we have things that are mostly the same as before. We have covariance with our intercept and slope. We have intercepts of I and S. This tells us the model implied expected baseline value for Y. And this is the expected value for Y when S is 0, or when the time score given S is 0, and when G and X are 0. And the slope is the same thing. It's the expected value of the slope when all the other predictors are 0. This tells us how much Y changes per unit increase in our time scores. So the change is about 0.7 for every time step. We have residual variances, which are similar to each other over time, so maybe we could be comfortable with a homoscedasticity assumption, but we don't necessarily need it. And we have residual variances for I and S. Last time when we looked at output, these weren't residual variances, they were variances. They're residual variances now because now they're dependent on X and G. But there's still an estimate of the variance in starting level and pace of change over time that's left over after accounting for the effects of X and G. Let's make a little change to the input file. Let's do output. And put tech1. This will give us the technical 1 output. This is going to give us the parameter specification of the model. So it's the same model, so I'm going to blow past all that and get right to the technical 1 output. Now we have our setup that has this is where Mplus is going to give us the technical information about the parameter matrices that are used to estimate the model. The first one is new. You'll remember from last time, you remember that new contains the means of the observed dependent variables. And those were going to be constrained to 0. Remember when we did longhand notation, we constrained all those means to 0. Now we've got something curious here, because we not only have y1, y2, y3, and y4 as our observed dependent variables, but we also have a column for g and x. And that doesn't make any sense, because those were supposed to be our predictor variables. So what's that about? Well, this is a thing that Mplus does to make its computations simpler when the input dependent variables are continuous. So when all the input dependent variables are continuous, it just assumes everything's continuous, because remember, it doesn't care about the scale of the predictor variables, and estimates a so-called Y-only model. It does rescaling that are necessary in presenting the outputs, but the way Mplus sets up the model behind the scenes is it assumes that everything is a Y variable, and we're just explaining covariance among the Y variables. But I wanted you to see that, because if you ever needed to look at your technical information, you might be a little bit confused. So lambda contains the factor loadings, and also you see we have latent variables. So the structure of lambda is observed variables by latent variables. And now we've got something even more curious. So we already talked about why we're going to have a g and x as observed dependent variables, but now we've also got g and x set up as latent variables. And that's really weird. And the reason why Mplus does this is because we want to relate our independent variables to our dependent variables. And the only way to do that is to assume that the independent variables are measures of single indicator latent variables. So again, this is just a technical thing that Mplus does to make its math simpler, but you need to see it so you don't get convinced you're doing something wrong when you have to look at your technical output when you're doing it on your own. And when you switch to categorical dependent variables, Mplus doesn't do this anymore, and does a different parameterization of the model. So that's the important things I wanted to show you about the technical 1 output. Okay, so one thing about that model that we just ran is we did a model where we explored mean differences in intercept and slope according to levels of G. Now let's just say, for example, this is a study of depression. We have repeated measures of depression. We have men and women represented by G, and we think that maybe there's going to be some difference in the variance of depression by men and women. The way they change over time may not be as strongly related to where they started out across men or women. That kind of thing is hard to test in a so-called single group model or with interaction terms. But we can do it very easily with a so-called multiple group model. And what a multiple group model is a model where we estimate a model in multiple groups simultaneously. We allow for some things to be the same across group, and some things are allowed to be different across group. And we can be very flexible on what we allow to be different across group. To see how to set up a multiple group model, let's get out the Mplus Users Guide. So everybody's got a downloaded copy of the Mplus Users Guide. And how we do everything with Mplus, whenever you want to do a new type of model, is you find an example in the user's guide and hack it to suit your own needs. So let's look at example 5.14. That said multiple group. So here's an example from the Mplus Users Guide. It's a multiple group analysis. This is a confirmatory factor analysis, but that doesn't matter. What I'm interested in is knowing what's the right syntax for calling for a multiple group analysis. And one key aspect of the command is specifying the grouping variable and giving labels to it. So we're going to want to do that. So I'm going to copy that out of my Mplus Users Guide and put it in my variable statement. And so the grouping subcommand identifies the variable that's going to be the grouping variable. And so G fits from the previous example. And we're going to use levels 1 and 2 for male and female. I'm a little bit concerned that that's not quite exactly going to fit our data set. So let's take a look at, G is scored 0, 1 in our data set. So we're going to have to make a little bit of an adjustment here where 0 is male and 1 is female. So let's go back to the Mplus Users Guide. The model command is a little bit different. It has an overall model statement, and then it has group-specific model statements. And so things that are in the overall model statement will be similar for both groups, and then we can allow some things to be different across those two groups. So let's go back to our Mplus, and we'll add a model. Model female. Here we could allow some things to be different across group. But here's the question. How do you know what to be different across group? Is everything going to be the same across group, or is something's going to be different? And this is where you need to know Mplus defaults. Mplus by default will set some things to be equal across group and allow some things to be free across group. And it's very tricky to learn what the Mplus defaults are. And once you learn them for multiple group analysis, you'll have to learn them again for latent class analysis. which is analogous to multiple group analysis, but the grouping variable is unmeasured. You'll always have to make sure you understand carefully what the defaults are, and I often code everything the way I want it and not rely on defaults because the defaults are different for different model setups. But let's run this model and just see what Mplus is giving us to be different by default before we specify anything. So I'm going to leave the model female blank for now, and let's see if Mplus will take that. Before I hit run, does anybody have any questions? Yes, so the question is, do you need to take G out of the model statement? And the answer is yes, you do need to take G out of the model statements. Thanks. Any other questions? These things won't get cut on the video. I'll cut out that. I'm going to skip right to me doing it right the first time. It's important to take G out of the model statement if it's being now used as a grouping variable. Don't forget that very important point. All right. Let's click run. Okay, input reading went normally, so that's a good sign. So now, in our summary of analysis, now we have two groups. Now we're running a two-group model. Mplus is going to repeat our labels, so male and female, and tell us the sample size for the two groups. Other aspects of the model will be the same. Oh, here's a variable with special functions, grouping variable G. And the model estimation terminated normally. That's wonderful. Well, we've got our model fit. Model fit looks slightly worse. It's interesting. Here's our chi-square contribution from each group. So chi-square contribution is a little bit larger for female. Whether or not that means the model doesn't fit as well for females, you have to be a little bit careful with, because a chi-square statistic is sample size dependent. So let's go back up and look at the sample size distribution. We have fewer females and more males. So if anything, that chi-square would be higher for males on the basis of sample size and lower for females. So the fact that we've got relatively equivalent sample sizes and a higher chi-square contribution from females means there may be something about this model that's not fitting the same for females. It might be worth exploring. So the first thing to notice in the model results is a subheading here under the results called group male. So the first set of results we're going to get are relevant to males. And we've got our fixed parameters for the growth part of the model. We've got our regressions of intercept and slope on our continuous predictor variable, and our covariance of intercept and slope. Our intercept values, so our mean expected value of intercept in males when time is 0 and x is 0, and our average change over time, linear time steps, is here in S when x is 0. We have our residual variances, our intercept, and our slope residual variances. Then we have the results for group female. The fixed parameters will be the same across group. Here's our regression of I on x. That's 0.943. That seems a little bit higher than it was in males. It was 826 in males. S on x is 0.433 in females, and it was S on it 0.420 in males. So that seems very close. And We have our covariance, S with I is 0.289. That seems lower, much lower. So there's much lower correlation. This is a covariance parameter, but we can say there's lower correlation between S and I among females. We have higher mean starting level for females and faster slope for females. So in males we had 140 and 0.698, and here we have 1918 and 0.0977. So here's our group male results. Here's our group female results. And so we've got the regression of I on X is different across males and females. And so this is analogous to an interaction between the regression of intercept on X by males and females. So that's how we would have done it with an interaction term in, say, something like proc mixed. Here we're just doing it in a multiple group framework. The parameter estimate you would get for that interaction effect in a proc mixed analysis is going to be equivalent to the difference between 0.943 and 0.826. Here we have S on X, which is about the same. Again, to get an estimate of the significance of this in our proc mixed analysis, we might do a three-way interaction of time and X and sex. And that parameter estimate would be equal to this difference here. And the covariance parameter also looks different, and I know it's got to be possible to do it with SAS proc mixed when you get into the covariance parameter specification, but that sounds hard. I'm sure somebody who's very good with proc mixed could do it. And so our intercepts are different. The intercepts for our intercept factors are different. That's confusing. But our estimated values at baseline are different. They're higher in females and lower in males. And the change over time is higher in females and lower in males. And the residual variances are slightly different in males and females. And the residual variances are also slightly different. How different these are will require some special tricks to do some model comparisons. But what did we learn about the Mplus default? So it looks like everything's different across sex. Is there anything here that's the same? The residual variances are different. The intercepts are different. The covariances are different. The regressions are different. The only thing that's the same is the specification of the time steps. We could start imposing some constraints on this model to try to let some of the things be the same across group. And the reason why you might want to do that is you might want to zero in on what specifically is different between males and females in growth and change over time, rather than just treating them as two completely different samples. Let us go back to our input statement. And let's start putting in some constraints. So let's say we wanted to assume that the residual variances of the Y's were the same over time and across sex group. So we'll assume homoscedasticity. We do that. The way you refer to variances and residual variances in Mplus is just to name a variable by itself. And I'm going to put a label here. I'm going to call it PSI. And I'm going to put a semicolon there. So now I've assigned a label to the residual variance for Y1. And anything else that I give that same label to now they'll be held equal to each other when Mplus does its estimation. That's called an equality constraint. And so right now what I've done is I've set y1 and y2 to be equal to each other. And I can do this for all of the residual variances by using a dash. So now I've assigned the label PSI to all of the residual variances for y1, y2, y3, and y4. And this will probably put the constraint in both males and females, but I don't know for sure. So let's check. I'm going to run this. So here's my residual variance for males. It's 0.503. So those are all the same value. And I've now gained 3 degrees of freedom. I can do stuff with that, like estimate other parameters. And let's look in females. And here in females, the same parameter constraint goes in group females. So if you wanted to know if that model modification changed your fit, you can do that by doing a chi-square difference test, where you would get the chi-square from this model, the chi-square from the other model, get their difference, get the difference in the degrees of freedom, and compare those to a chi-square table or a function in your computer. You can also do it with the change in -2 times log likelihood. I'm not going to do that today, but just eyeballing it, it looks like the model fit is a little bit worse, but it doesn't look like it's all that much worse. I think we had 14 and change last time, and now we have 19. We have 3 degrees of freedom, so I'm going to say that's a non-significant worsening of model fit. The p-value for that change would be greater than 0.05. If this were real research I was going to publish, I would do this formally, test this, build your little spreadsheet or whatever you need to do for your different models. So now we can do, let's do something that might not be a non-trivial difference, and put in a constraint on the covariance of the intercept and slope. And you refer to covariance parameters with the with keyword. So this I with S refers to the covariance of intercept and slope. Doesn't matter if you say I with S or S with I. Oh, but let's put a label on it. And I'm going to call that PSI-SI. Does anybody know why I'm calling these PSI? Yes, very good. The answer is because the psi matrix is the matrix that holds the variances and residual variances from the regression model. What else could I have used there? Right? I could have used anything.
I like that just came into your head.
I can't get it out of my head. Okay, so this model runs, and the chi-square is worse, but it's a trivial difference. We're up about 2 chi-square points, and that was 1 parameter, so that's 1 degree of freedom. We were estimating 2 covariance parameters, now we're only estimating 1, so that's a 1 degree of freedom test. So even though those covariance parameters look different, covariance parameters have a lot of variance. They're hard to estimate precisely, and what looks like a big difference might not actually be a big difference. So let's do something that needs to be different across group, just for kicks. Let's say that let's look at this command that was the same across groups. Let's say all the girls came in for their last visit at 2.5 years, not 3 years. Because they had to go on a field trip to the Taylor Swift concert, and they needed to be excused from the protocol early. So we're going to change their last time step to 2.5, reflecting our design. And now we've got something that should be different in males and females. We'll run this, put terminated normally. And we've got our group male model results here, where the last time step is 3. This comes from the overall group. And we'll scroll down to the female results, and here the time step for the last step is 2.5, as we specified. And I hope they enjoyed the concert. This is a pretty big hit to chi-square, by the way. All right. So let's take this off. Rich, that's great. I really like seeing how you do latent growth curve modeling with covariates, but let's say I want to write up my paper and I want to have some standardized results, or I want to describe these things to my readers in an interesting way. Oh, that's a piece of cake. Good question. Here's how we do that. Go to Output and ask for standardized output. Now, in your Mplus Users Guide, so here's the output command in the back of the Mplus Users Guide, and there's different ways to specify standardized output. You could say stand, you could say standardized, you could say standardized parentheses all, or you could say standardized STDY or standardized STD. The default is all. When you ask for all, you're going to get these 3 flavors of standardized output. This was on the quiz, if you remember, from the first session. I'm gonna get all 3 because I'm interested in all 3, and I'll show you why. Sometimes you may be okay just getting the STDYX output, but we're going to use all 3 today. So I'm just going to leave this standardized here. Standardized. Stand.
Where did the model females go?
I don't know. I think I just took it off. I think I'll leave it off. I don't think I'm going to need it because I've got some constraints, and I'm not going to allow anything. I'm not going to the overriding of the faults. I'm going to do that. I could take care of in the overall model statement. But if that's wrong, Mplus will let me know. Any questions before I hit run? Okay, I'm going to call this up in the browser again so I can blow it up. So the model went fine without a specific model female statement. I should say, by the way, you can have a general statement, then you can have model female, and you can also have model male. If it makes you feel good to put specific things in specific models, you can definitely do that. You must have the general model statement. But after that, you can get flexible and you can include a model statement for both. And I code in what I like to call belts and suspenders fashion, which means if there's any doubt in my mind as to what Mplus is going to do, I code it specifically. And I just find that ends up saving time because I can limit my trips back to the Mplus user's guide or take the risk of making a mistake and not noticing something in the output that I assume is the way I think it should be, but isn't actually that way. Okay, so we've run this model before, but we want to look now at the standardized output. So here's the output we looked at before: model results, group male, group female. Now we have a new section here called standardized model results. And the first section of the standardized model results are the STDYX standardization, which is, these are model results that are standardized with respect to the means and variances of the observed and latent variables. And some of this is going to be useful and interpretable, and some parts of it we're going to choose to ignore. Like, for example, we can ignore these standardized model results in the measurement part of the model. But here we might be interested in the standardized results for the regression of I on X and S on X, because these now tell us the standardized relationship between our continuous predictor variable and these continuous latent variables that are intercept and slope. And so these are saying that for every standard deviation increase in X, there's a 0.54 standard deviation difference in I. And these are on the scale of correlation coefficients or regression coefficients from a fully standardized linear regression model. And also, this I with S parameter now is this is a covariance parameter, but because everything's standardized, this is on the scale of a correlation coefficient. So now we can say that baseline and pace of change over time are correlated at 0.4. Now my personal preference in looking at standardized parameter estimates is to report these as effect size statistics. But if I wanted to say if this covariance parameter, for example, was significant or not, I would go back up to the parameter estimate and get the standard error and the z-test associated with the unstandardized coefficient. You'll see the unstandardized coefficient has a z-test value of 10.6, and the standardized value has a value of 9.5. Those are different now because these standardized coefficients now incorporate the variances of the things that we're estimating. And I think that mixes it up. And it's not so much a big deal here for a covariance, but sometimes you'll be looking at regression coefficients, and for those it might be different. Let's see if those are different. Here's our regression coefficients of about 15.8 in the two models, and they're a little bit lower in the main models. So do your inferencing with the unstandardized model results and use the standardized results for effect size description. I'm going to go back to Mplus, to the input statement. I want to leave the multiple group framework for a second. I want to go back to treating G as a predictor variable. So I'm going to comment out this grouping is line, and I'm going to add G back to my list of predictor variables for I and S on X. So what I did is I put an exclamation point here in front of grouping, and then I added G back here as one of the predictors of I and S. Everybody with me? We're going to run this. So when we look at the standardized output, let's see. Here's our stdyx output. And now G appears back here as a predictor of I on G. So this is the stdyx output. This is standardized, fully standardized we call it. Standardized with respect to the mean and the variance of the observed and latent variables, exogenous and endogenous variables, independent and dependent variables. And so this parameter here, this 0.163, tells us the standard deviation difference in I per standard deviation difference in X. Or G, excuse me. This parameter here tells me the per standard deviation difference in I per standard deviation difference in G. And remember, G is 0, 1, male, female. And so what's a standard deviation difference in male or female? It's a little bit hard to say. So this standardized parameter estimate isn't going to be helpful as a descriptive variable. But STDY, which is standardized, the X is missing from that, right? STDY. So now we're no longer standardizing with respect to X. So here, the I on X is 0.5, no, I on G, excuse me. I on G here is 0.326. This is saying that a unit difference in G going from 0 to 1 is associated with a 0.326 standard deviation difference in I, which is our estimate of Y, the baseline Y1, given our linear model. So the multiple group model can be useful sometimes. The multiple group model is useful in clinical trials. So rather than regressing on a dummy variable indicating randomization status, you can do a multiple group model for randomization status. And you can specify the treatment effect with an additional latent variable, and that can have so the treatment effect can have a variance, so people can differ in their treatment response, and you can look at how predictors relate to that treatment response. And there are examples of how we do that in our short course handout, our 3-day short course handout. Okay, let me repeat for people on the phone. The question is, what's the advantage of doing a multiple group model versus a simple covariate model? And the short answer is you just get more flexibility with a multiple group model, and if it fits your design and you can make use of it, a multiple group model gives you that added level of flexibility. One particular way where it's very useful is in the analysis of randomized controlled trials. But we did an example where the time scale was different for people in the two groups. And that's one thing you can do with a multiple group model that you couldn't do. And so it's just an added level of flexibility. Sometimes it's useful, sometimes it may not be useful. I'm gonna hold off in doing a clinical trial example and go to our next example.
Rich,
Yes.
Before you move on from standardization, when do you use STD?
I don't think I've ever used STD. I guess not. So using STD standardizes with respect to the observed dependent variables, but not the latent variables, or the latent variables and not the observed. I forget. It was on the quiz.
I think it's the.
Who took the quiz?
I think it was the late. Or at least that's what you said last time.
Okay.
Standardizes for the latent.
Well, yeah, STD uses the variances of the continuous latent variables for standardization. So it's only standardized with respect to the latent variables. So this would be a case where you didn't want to standardize the dependent variables, you cared about their variances, but you still wanted to have latent variables that were on a mean 0, variance 1 metric, like in factor analysis. Insert good example here. When you deal with categorical dependent variables, you'll often see that the STD-Y and the STD are similar, and that has to do with the fact that the variances for categorical dependent variables aren't separately defined from their means, so standardizing on them doesn't impact the output. Okay, so now we're going to look at example 6.12. So we're not exactly going to do what's in the Mplus User's Guide for example 6.12. We're just going to use the data set that is provided with example 6.12. What we're going to run through today is how to do growth curve modeling with Mplus when you have individually varying time points of observation. So people may in general follow a 0, 1, 2, 3 schedule for their assessments, but not everybody comes in exactly when they're supposed to, and we want to have our analysis model take into account the fact that there may be some variance in how people adhere to the per protocol design. Or let's say it's a purely observational study and you don't really have any control about when people come in, and you want to use the times when you actually observe people in the analysis. Okay, so here's an example of a growth curve model with individually time points of observation. The data file is example 0612.csv. The names statement tells us about the names of the variables in this data file. There's a new subcommand here called t-scores. T-scores is an abbreviation for time scores. I don't think you can unabbreviate time scores. You have to put t-scores. And here we're naming 4 variables that contain the data that tell us about when the observations happened. So as part of your data preparation step in SAS or SPSS or R or Stata, you have to not only spit out the repeated observations you want to do the analysis on and the predictors you want to include in the analysis, but you also now have to spit out a column of data that contains the timing variable. And you need one for each observation. And these t-scores are A11 through A14. You can call these whatever you want. I usually use T1, T2, T3, T4. In the use variables subcommand, I'm going to restrict this analysis to just the repeated observations and when they were observed. Now the next command is the analysis command. We haven't seen this before, I don't think. In this command, we can tell Mplus specific things we like to change about how it does the analysis. And when I mean change away from defaults. And here we're asking Mplus to do a random effects model rather than a latent variable growth curve model. And so all we need to do to use our individually varying time points of observation data is identify the t-scores, ask for type equals random in analysis, and change our model statement to make use of those time scores. And so here we have our model statement, and you must use shorthand notation here. There's no longhand notation version of this. We say IS. These are our latent variables or our random effects. And the indicators of these random effects are Y1 through Y4. And the time points are here at A1 through A14. Hearing none, I will run. So here's our output statement. We get our analysis spit back to us. Variables with special functions here. This is something new. Time scores, A11, A12, A13, A14. Model estimation terminated normally. That's a good thing to see. Here's our model fit information section. Notice that this section is very much reduced versus what we got last time. It's very much reduced because we've left the structural equation modeling framework and those CFIs, TLIs, RMSEAs, and chi-square statistics all derive from the structural equation modeling framework. And now we're in a random effects modeling framework. And so we're just getting log likelihood statistics and information criteria to assess model fit. We have to use the same kind of tricks you would use if you were using SAS-Proc mix to try to figure out if your model fit well. I like to use the empirical R-squared or pseudo R-squared. This is described in Singer and Willett's book, 2003, Applied Longitudinal Data Analysis. Basically, we're going to get Mplus to save out our predicted values for the intercept and slope, use those to predict values for the repeatedly observed y's, and then correlate our model implied y's and our observed y's and get an R-squared for the model and declare that that's a good fit, because there's no guidelines to decide what's a good fit or not. So if it seems high, well, it's good. And we also break that out into subgroups and look and see if it's not fitting particularly well for specific people, calculate some residuals and look for the distribution of the residuals overall and in specific subgroups to convince ourselves that it's a well-fitting model. Okay, so here's our model results. We no longer have this section that I would call the measurement model before. And that's because we're no longer having these fixed time steps. All that's taken care of in the black box that is Mplus. And it's not available to us as output here. We go right down to our covariances of our intercepts and slopes, our means for our intercepts and slopes. We do have our intercepts for our repeated y's, and our variances for our intercepts and slopes and residual variances. And then everything else is the same. We can add a predictor variable. So I'm going to add a x to the use variables command. And I'm going to see if x is an important predictor of intercept and slope by regressing both intercept and slope on x. And that's just like it was when we did it before. And the output is telling us that yes, it's true. X is an important predictor of intercept and slope. So, the question on the floor is, when would you use time scores versus fixed? If they're generally uniform, I would use the fixed time scores. If they're widely varying among people, I might use the random effects time scores approach that we just covered. Also, it depends on where I want to send it. If I'm going to send this to a psychology journal, and then I'm going to tell them I used Mplus and latent growth curve modeling, I'm going to try really hard to use the fixed time scores approach, because the reviewers there are going to ask me what my CFI and my RMSEA were. And if they don't give that to them, they're going to feel like I'm cheating. But they're just not available for the time scores approach. And not everybody uses Mplus, so they don't understand that. And I don't want to cause any hard feelings. So I'm going to try harder to use that when I'm going to a psychology journal. When I'm going to a medical journal, nobody there knows anything about structural equation modeling. And so they're not going to be upset by the absence of those model fit statistics. This is a little bit of an overgeneralization, but that's usually how I think about it. And if I can say I did a random effects regression using, I'll say I did a random effects model with individually varying time points of observation, and parameter estimates were obtained with Mplus software. They don't have to get into the detail of latent growth curve model. People, once you start saying latent, people start going, what are you talking? What's latent? What does that mean? Never mind that the random effects and the latent variable occupy the same conceptual space, or the same thing. So I'll tweak it depending on where I'm going to send it. Okay. Well, I'm going to stop us. We're about 3 minutes early. Thank you, everybody, for coming. Have a nice holiday break. I'll see you again bright and early in January the 7th, I believe. January 7th. Oh, this is going to be good. We're going to talk about exploratory data analysis and graphics and evaluating model fit. So we'll cover the interpretation of the model fit next time, but we're also going to talk about things you might do before you go to Mplus.